I'm Michelle Jordan, and today we're going to do 7th grade Eureka Math, Module 2, Lesson 2. Okay, today we're doing Lesson 2, and we're going to be using a number line to model the addition of integers. Exercise 1. Suppose you received $10 from your grandmother for your birthday, and you spent $4 on snacks. Using addition, how would you write an equation to represent this situation? And so first of all, we have to know what they mean by writing an equation. So we're going to be writing a problem that has an equal sign. So the first thing we know is that we received $10. So that's a good thing, right? We have $10. Then we're going to spend 4. Do you think that that would be a positive or a negative thing? It's a negative thing. So if we're doing an addition problem, we want to use a plus sign. But we need to represent spent 4. And so representing that would be a negative 4. Okay? So if you have $10 and you spend 4, how much do you have left? You have 6. And another way you can think about that would be 10, take away 4, and you have $6 left. But part B says, how would you model your equation on a number line to show your answer? So if it's asking you to model your equation, you're going to be using a number line, whether they give it for you or you have to create it for yourself. So we want to represent this using vectors. And vectors will just be arrows. That's a fancy way for the arrows. So vectors show direction and unit length. So our first number in our equation is 10, and this is a positive 10. And so remember that we always start with 0. So I'm going to start close to the 0 here, and I'm going to go to the right, because that's a positive direction, 10 units. And then I stop right here at 10. My next number that I need to represent in my equation is negative 4. So if I start right here where my tail stopped, which direction do I need to go if I'm representing negative 4? I have to go to the left because that's what direction negative numbers belong. So 4 units, so there's 1, 2, 3, 4. So my second vector stops at 6, which is represented in my equation. Example 1, modeling addition on the number line. Complete the steps to find the sum of negative 2 plus 3 by filling in the blanks, and then model the equation using straight arrows, which are called vectors, on the number line below. So unfortunately, our number line is on the back side of this. We're going to place the tail of the arrow on 0. The first number we need to represent is negative 2. So draw the arrow 2 units to the left of 0, and that would make us stop at negative 2. The direction of the arrow is to the left since you are counting down. So counting down, that's negative from 0. So let's go to our number line, which is on the next page. Okay, so we're going to model that problem on this side. So you had to flip over negative 2 plus 3. So I'm going to rewrite this. So the first number we need to represent is negative 2. We will start at 0. We will go to the left 2 units with our vector, and then we will stop there at the end of negative 2. On D, draw the second arrow 3 units to the right since you are counting up. Counting up is positive from negative 2. And where will we stop at? So let's look at, for our second number, we will do a positive 3. So we're going to start with our tail of our vector at the negative 2 where we stopped. We will go to the right 3 units, so 1, 2, and 3. So 1 unit, 2 units, 3 units. If you need to draw yourself some bunny hops or count the gaps in between to count your units, that's okay. And then we can see that our line stops at 1. The process from parts A through F for the expression 3 plus negative 2. So this time we see this word expression, and the difference between an expression and an equation is an equal sign. So let's repeat. The first number we need to represent is 3. So we're going to start at 0. We're going to go to the right 3 units because it's positive 3. So that's our stopping point, is that positive 3. The second number we need to represent in this expression is negative 2. So we begin where we left off, and this time we're going in the left direction 2 units. Our stopping point here is 1 also. So what can we say about the sum negative 2 plus 3 and 3 plus negative 2? Does the order matter when adding numbers? Why or why not? So in the first one, we represented negative 2 plus 3. And in the second one, we represented 3 plus negative 2. The difference is that the vector for this one was 3. That's the first vector. And the first vector on this one was negative 2. So we changed the positions of the vectors. But in our answers, you can see that we get the same result. So does the order matter when we add numbers? No, order does not matter. And then why or why not? Addition is commutative. Commutative means it moves positions. So whether it's 2 plus 3 or 3 plus 2 or any combination of integers that are positive and negative, the order does not matter as far as the answer. The order does matter when you draw your vectors because they want the first number to be represented as close to the number line as possible. Expressing absolute value as the length of an arrow on a real number line. How does the absolute value determine the arrow length for a negative 2? So absolute value, to review that, absolute value is the distance from 0. So it doesn't matter if it's a positive direction to the right or a negative direction to the left, it's how many units that number is away from 0. And so how does absolute value determine the arrow length for negative 2? Use the number line provided to support your answer. So let's represent negative 2 on our number line. We start with our tail of our vector at 0, and this time we will go to the left 2 units. And this would be our stopping point. How many units from 0 is it? Well, it's 1 unit here, 1 unit here. So the absolute value, these are the symbols that we use for absolute value, just 2 straight lines, is 2 units. How long is our vector? 2 units. Look at our next one. B. How does the absolute value determine the arrow length for 3? Use the number line to support our answer. So again, if we wanted to represent the number 3, we would start with our vector tail at 0. We would go to the right 3 units and we would stop. So the absolute value of 3, 1 unit, 2 units, 3 units. How long is the vector? 3 units. Determine how the absolute value helps you represent negative 10 on a number line. So this time they don't even give us a number line, but using the first 2 that we just did, what would the absolute value of 10 be? 10 units. Absolute value doesn't have a positive or negative. It is simply a count of units, and distance is not positive nor negative. So a count of units, 10 units. The vector will be 10 units long. Exercise number 2. Create a number line model to represent each of the expressions below. So remember that we have to start with the first number that we're given when we're representing vectors. So we're going to start with negative 6. So we go from 0. We will go to the left 6 units. So 1, 2, 3, 4, 5, 6. So we stop at -6 for the first. Then we need to go which direction? Right? How many units? 4. And where do we start this at? Started at the -6. So we're going to go to the right 4 units. So 1, 2, 3, 4. Where do we end up? -2. Let's look at this one. First, we need to represent +3. We start at 0. We go to the right 3 units. So 1, 2, 3. That puts us here at 3. Then we need to go to the left 8 units. 1, 2, 3, 4, 5, 6, 7, 8. And that puts us at -5. Find the sum of the integers represented in the diagram below. Part A, write an equation to express the sum. So an equation means that we're going to have an equal sign and we're going to have an answer to the right of the equal sign. So the first thing we want to do when we look at this number line is we look at the vector that is closest to the number line, which will be on the bottom. This is the first integer that we need to represent. So it starts at 0 and it ends at 5, and we can see that they've labeled it with a 5. We are working with addition here today, so plus. Notice that we have 3 vectors, so we're going to have 3 terms in our equation. The second vector starts at the end of the 5 and moves to the left 2 units, and they have that represented for us with a -2. Notice that I'm going to include parentheses. These parentheses help to separate the addition sign from the negative symbol. And then we need to represent our third vector, which will be on the very top, and that is a +3. Now, since it's an equation, it needs an answer, and so let's see where our final vector or our top vector ends up. The head of this vector stops at 6. So that's our equals. What 3 cards are represented in this model? So if we were playing the integer card game and each card has an integer on it, these would be the 3 cards. And so we would have 5, -2, and 3. And how do we know this? We looked at the vectors. In what ways does this model differ from the ones that we used in Lesson 1? So if you remember back to Lesson 1, we used bunny hops or lines like this, arrows like that, not straight arrows. And so this one counted each individual unit, whereas today we've been using these straight arrows to represent our integers. And so even if you don't use words, if you can use a drawing to explain yourself, that'll be fine. And so I think this represents our answer quite well. Part D. Can you make a connection between the sum means to do what? Add, of 6 and where the third arrow ends on the number line. So the sum is 6, represented here, and where the third arrow ends. So 6 is the stopping point of the vector head. Would the sum change if we change the order? So let's go back to what we said a minute ago. We said that addition is commutative, which means that the numbers in the problem can move orders and the answer does not change. So would the sum change if we change the order of the numbers? For example, if we moved the -2 first, then the 3, and then the 5, does the answer change? So no, addition is commutative. They don't ask us to explain, but that's a good idea. Commutative. would the diagram change? So we talked about how the order matters in the diagram because our first vector is 5, our second vector is -2, and our third vector would be 3. So if we change the order here, our vector order also changes. So yes, the vector order changes. We would have to represent -2 first, then 3, and then +5.